The history of Earth began exactly 13.7 billion years ago with the occurrence of the Big Bang. Pleonastic statement and therefore difficult to refute since everything that exists in this part of the universe, nothing excluded, was born at that precise moment. Even the smallest particle of matter that is now part of the Earth maybe ended up in a molecule in the eye of a swallow or on top of the Andes Mountains, was formed 13.7 billion years ago, and it has come down to us through twisted and mysterious ways. As mysterious are the transmutations that every molecule of our body had to endure before arriving here to open our eyes to that universe from which we come. We are made of the same stuff as the stars, indeed wrote astronomer and popularizer Carl Sagan many years ago. But we now know that half of that dust comes from stars far, far away, even outside our galaxy. But if everything started at the moment of that famous T with zero, it remains curious to know at least a couple of things. When did the universe begin to resemble what we know today? And ultimately, when did galaxies, particularly ours, and then stars and Earth, form? A few seconds after its birth, all the existing must have had the consistency and appearance of a hot primordial soup of particles, especially electrons, protons, and photons of light, a kind of opaque fog, where photons could not travel significant distances without colliding with electrons. Just as a ray of light in a fog bank is immediately intercepted and spread by some droplet of water in suspension, thus forming the typical wall effect. For this reason, this phase is called Dark Age of the Universe. Lasted until 380,000 years after the Big Bang. All space suddenly became transparent to light radiation. From that moment on, in fact, in an environment where the temperature had dropped a lot, facilitating the combination of electrons and protons of the first hydrogen atoms, collisions between particles became extremely rare, and photons began to travel freely. Since then, hundreds of millions of years would pass before atoms joined, giving birth to the first generation of stars, which, evolving through the fusion of light primordial elements, hydrogen, helium, lithium, would have synthesized carbon, oxygen, and iron, all heavy elements that then, once diffused in the interstellar environment by the explosion of mother stars, would go to enrich the stars of subsequent generations. A process that has always continued and still continues. Astronomers have long wondered if after the Big Bang stars appeared first, condensed from small nebulae, or if galaxies were the first to form from much larger nebular structures. Today, there are well-founded clues to think that the first hypothesis has occurred. Stars were born first, then aggregated in globular clusters, which in turn would have joined to form the first galaxies. All this between 400 and 700 million years after the Big Bang, about 13 billion years ago. At that time, our local universe, or whomever handed us a legacy made up of 2 trillion galaxies, later diminished in number by continuous mergers. One of these was our own Milky Way. We cannot know if the Milky Way of that time was exactly identical in shape and size to the one we live in now. More dusty perhaps, with a smaller and thicker disk and a denser halo, and also much more active in new star formation, but substantially similar to what we can see in photographs depicting one of its near twins, namely the Andromeda Galaxy. According to current measurements, the visible part of the disk, excluding the diffuse halo that surrounds it, which is much larger, could have a diameter of 120,000 light years. Said in this way, the thing may not impress much. It is not so immediate to be able to give a meaning to such a measure, and even it would help to know that 120,000 light years corresponds to 1.15 billion of kilometers. But a small example will help us to better understand what we are talking about. Let us imagine to build a scale model of the Earth-Sun system in the Milky Way. Suppose, for example, that 1 millimeter corresponds to 1 million kilometers. In order to represent the Sun in this scale, we will have to get a small ball of 1.5 millimeters, while the Earth will be represented by a particle of dust placed at a distance of 15 centimeters from it. Up to this point, no difficulty, but things would be complicated a lot if we really put to build the outline of the galaxy. To represent it, in fact, in the same scale, we would have to put ourselves to build a disk with a diameter of about half a meter, 50 meters? No, 1.2 million kilometers. Yes, you got it right. In our model, the galaxy should have a diameter equal to 4 times the distance that separates us from the Moon. And if in the same scale we wanted to represent also its distance from Andromeda Galaxy, which is our neighbor, maybe it would be better not to think about it. The real distance is in fact 2.5 million light years, so we should place the disk at 25 million kilometers. And in front of this enormity, we face one of the most frequently asked questions in astronomy. How many stars are there in the Milky Way? A question that is not easy to answer. There are different estimates, ranging from the classic 100 billion of some time ago to 400 billion today. The problem is that in the impossibility to see and count every single star, the best thing we can do is to calculate the total mass of the galaxy, deduct the component consisting of gas and dust, but even here the evaluations are very different, not to mention the variable not very quantifiable introduced by the presence of dark matter, and divide the result for the mass of an average star such as our Sun. With this system, we can estimate that the number of stars amounts to 110 to 170 billion. But who says that the Sun can really be considered the prototype of the average star? Apparently, in fact, only 5% of stars are G-type, that is, main sequence stars like the Sun, while 80% of stars in our galaxy are red dwarfs. This, considering that a typical red dwarf has a mass equal to 1/10 of the solar mass, would bring the number of stars present in the Milky Way to very close to 1 trillion. But in addition to the stellar component, galaxies still young as the Milky Way have an abundant set of gas and dust that is generally called interstellar matter and is formed mainly of hydrogen, with a smaller percentage of helium and traces of gases such as carbon monoxide, ammonia, methane, and water vapor. This gas tends to thicken in clouds extended for tens and hundreds of light years and can be in different states. There are in fact clouds of neutral hydrogen in the molecular state, very cold and dense, clouds of neutral hydrogen atomic state, more rarefied, and clouds of ionized hydrogen, hot and rarefied, all with its own color, from red to blue, dictated by the conditions of matter and the proximity more or less pronounced with very hot stars in formation. Nebulae, in fact, can shine with their own light because inside them there are stars that emit large amounts of energy that can heat the gas. They can reflect the light and color of nearby stars, and finally, when composed of dust, can absorb the light of the background stars, appearing as dark masses that stand out against the bright background of the Milky Way. The spectacle of light and color that they can put on stage is truly remarkable. But in reality, these clouds are composed of extremely rarefied matter, with a density of a few atoms per cubic centimeter. If we were inside them, we would probably not even notice. But it is precisely from these clusters of almost empty that new stars are formed. In those regions where the density of gas following a gravitational perturbation becomes high enough to make it collapse, with a process whose duration can vary between a few 100,000 and a few million years, depending on the rate of accretion and the mass that the birth star can accumulate. It is estimated that a star similar to the Sun takes about 100 million years to form completely, while for the most massive stars the time is considerably less, in the order of 100,000 years. And it is precisely in a region distant from the core of the galaxy, about 27,000 light years, that 4.57 billion years ago, one of these nebulae began to collapse, thus starting the process that soon led to the formation of the Sun and our solar system. The cause of the collapse is not well known. According to the most accepted theories, it could have been the random transit of a massive star, or the shock wave triggered by the explosion of one or more supernovae in the vicinity. Whatever its origin, the effect of the perturbation was to fragment and thicken the cloud into hundreds or perhaps thousands of small globules, called Proplid or protoplanetary disk, each about 1/10 of a light year in size, more than 100 times the current size of the solar system. Inside the globule in which the sun was forming, the gas continued to collapse and heat up, with an interestingly pronounced rotation, as in the classic example of the skater that rotates faster and faster as it gathers on itself. All matter involved in the transformation process flattened out on the rotation plane, thus forming an accretion disk of about 10 billion kilometers in diameter and 100 million kilometers thick. Accretion that also determined a non-homogeneous distribution of mass, so the lighter materials are arranged outside the disk while the heavier ones remain close to the nucleus. After 2.2 million years from the beginning of the nebular collapse, the substances present in the inner region of the disk, favored by the high temperature, began to condense into small particles of dust. After that, the agglomeration process was triggered, which involved larger and larger particles of matter. At the beginning, they were aggregations favored by electrostatic forces. Then they passed to more and more frequent collisions, which led to the formation of much larger objects called protoplanets, similar in size to the Moon. At the end, from this cosmic billiards, in the inner solar system came out winners, only 4 planets: Mercury, Venus, Earth, and Mars, smaller than those we know today and continuously bombarded by rocky debris that still traveled through interplanetary space. A deluge of small impacts that caused their crust to continue to oscillate between the molten and solid states. The future Earth, far from being similar to the enchanting blue planet we know, was also in the same condition. It was an oblong-shaped ball of fire, crushed at the poles by the very high speed of rotation. The terrestrial day at that time lasted only 4 hours. These were the tormented phases, which in a little less than 100 million years led to the formation of a rocky planet such as our Earth. But in all this forming of new worlds, one wonders, where was the Moon? It seems strange, but our current satellite, certainly not a second-rate object, as far as we know, had not yet appeared on the scene at that time. How come? Is there an explanation that can account for this delay? Obviously there is. On the contrary, as always happens with big questions, in the course of time the explanations have multiplied, correcting each other and perhaps confusing the waters even more. At first, it was thought that the Moon was formed by fission, that is, by detachment of part of the outer material of the Earth due to the strong rotation speed of our planet. Then it was passed to the capture theory, which predicted that the Earth had captured gravitationally a passing planetoid. After that, in the 70s, took place the giant impact theory, already vaguely hinted in the past, and resumed with more method by Americans William K. Hartmann and Donald R. Davis in research published in 1975. Their proposal started from the assumption that 4.5 billion years ago, the inner solar system still hosted many celestial bodies of subplanetary mass, and that the impact with the Earth of one of these objects, that only many years later in 2000 would have been called Theia, as the mythological mother of Selene, could have thrown in the space materials that would have then aggregated to form the Moon. Things, according to the two researchers, could have gone like this. While the young Earth was still there, shapeless and hot, continuously targeted by small and tiny planetoids, here is that 4.51 billion years ago, suddenly loomed the collision with a real planet about the size of Mars. Theia hit the young Earth at the speed of a few kilometers per second. The impact was inelastic, with the almost total transformation of kinetic energy into heat, and the ferrous core of the planetoid sank into the Earth's mantle until it merged with the Earth's core. At the same time, the portion of the mantle of Theia farthest from the Earth was spared from the impact and continued on its way, but perturbed by Earth's gravity, changed direction and entered the orbit of our planet, where powerful tide forces broke it into minute fragments. In a few hours, 80% of Theia was completely assimilated, while the remaining fraction went to form a disk of debris around our planet. The energy of the collision had generated a frightening amount of heat, so that the disk was eventually composed of gas, small particles, and molten rock, almost all material from the Earth's mantle, which is notoriously poor in iron. Other light elements evaporated and were lost in space, leaving behind rocks apparently devoid of volatile substances, but which, as the Apollo missions later demonstrated, still retained minimal traces of water. After that, the disk began to radiate heat into space, cooling down. In a few decades, the particles solidified so that the Earth found itself surrounded by a ring of rocks that extended up to 30,000 kilometers from its center, where materials and gases pushed up to the upper layer of the Earth's atmosphere. A possible explanation for this is why the isotopic ratio of oxygen of the Moon and Earth present today is so similar. Rocky particles began to collide and aggregate, becoming larger and larger, but the conditions for aggregates were only optimal where the tidal force of our planet was weakest, beyond the so-called Roche limit, located about 3 Earth radii away. The solid matter located beyond that limit quickly began to form larger and larger planetoids, which then, always by coalescence, in a few thousand years ended up giving shape and mass to a single celestial body, the Moon. Everything solved then? Not really. Although it continues to be the most followed one, recently the impact theory has seen the flourishing of alternative hypotheses, elaborated mostly by changing parameters like origin, composition, number, and mass of impacting bodies, or the values of incident angle, Earth rotation, speed, etc. Is all this uncertainty a sign that we must resign ourselves to consider the origin of the Moon as one of the many mysteries that we will never be able to penetrate? It may well be, but at the moment, it is enough for us to continue the story. The period of time immediately following the formation of the Moon corresponds for the Earth to the beginning of an era called Hadean, a term that sounds a bit like infernal, and that perfectly defines the era in which the Earth's crust began to form and the surface of our planet, still incandescent, had to look like a real hell. In this period, decisive for the history of the young Earth-Moon system, we do not have many certainties. It is believed, however, that from the incandescent rocks in the Earth's mantle, especially due to volcanic activity, began to release gases such as ammonia, hydrogen, carbon dioxide, methane, and water vapor, elements and compounds that within 100 million years went to form the primordial atmosphere. In any case, extremely toxic to life that we know today. At the same time, the heavy elements such as iron sank towards the nucleus due to the force of gravity, while the lighter ones, silicates, rose to form a glowing ocean on the surface. After about 400 million years after the impact of Theia, the material, more exposed, began to cool, and in the sea of magma began to form increasingly large rocky islands, the first signs of the future Earth's crust. A hell for real on Earth, but for the Moon, things were not better. At that time, our young satellite was not yet bound by that singular correspondence between the period of rotation and period of revolution that still characterizes it today. In other words, today the Moon always shows us the same face. But just after its formation, it was not like that at all, and a possible observer located on the primordial Earth could have seen night after night the Moon rotating on itself until showing its entire surface. According to some sources, in those times, our satellite, still red hot, was only 16,000 kilometers away from Earth. Therefore, it must have loomed over the Dantean landscape with an apparent diameter of more than 12 degrees. Can you imagine how terrifying its appearance on the horizon must have been? But having the Moon so close was not only frightening for the Earth's surface, it also meant being continuously crossed by tidal waves thousands of times more intense than today's, capable of lifting the still semi-solid crust for hundreds of meters. And it is easy to understand that in such extreme environmental conditions, it would have been difficult for our planet to evolve to the point of one day being able to host life. Fortunately for us, otherwise we would not be here to talk about it, it was the tidal force itself that slowly remedied this state of affairs, moving the Moon further and further away from the Earth. And this happened thanks to the progressive slowing of the Earth's rotation period due to the friction of the giant tides on the ocean floor. The most recent estimates tell us that the increase in the length of the Earth's day currently amounts to just a couple of milliseconds per century, while the Moon is moving away at the rate of a few centimeters per year, values apparently insignificant and almost beyond any possible verification, but that in the long run have led to upsetting changes in attitude. Numerous geological and paleontological analyses suggest, for example, that 50 million years after its formation, or 4.46 billion years ago, the Moon was 64,000 kilometers away from Earth, and the Earth's day lasted about 7 hours, while half a billion years later, the length of the day had already increased to 14.4 hours, and the Moon was now 282,000 kilometers away. In short, just after its formation, the Moon thought well to remedy its dangerous and cumbersome proximity, starting a phase of estrangement that still lasts, and that will continue in our remote future. In the meantime, the contraction of the protosun finally came to an end. The temperature of the nucleus reached, in fact, 15 million degrees, high enough to trigger nuclear fusion through the transformation of hydrogen into helium. So, the nuclear furnace is ignited, and from the sun is released a new form of energy, in the form of radiative pressure, that besides giving it a vivid brightness, it also generates imposing corpuscular winds that, crossing outward toward the whole solar system, end up sweeping away the residual dust that still made it opaque, interrupting with this any other process of aggregation. And so it was that 4.46 billion years ago, our Sun entered the so-called main sequence phase, the longest and quietest period in the life of the star of its type. 4 billion years ago, about 500 million years after the birth of the Earth, the dissipation of heat into space began the cooling of our planet. And in the ocean of magma began to appear flaps of rocks formed by minerals with a high melting point. A kind of hot but solid rafts, similar to the thin crust that we see forming on the surface of a lava flow, while it is still flowing from the crater. Then, the lowering of the temperature below 1000 degrees allowed the consolidation of the less hot areas, which became more stable and started the construction of the future crust of the Earth. But those very first fragments of crust had to be also very unstable, and they had to be easily reabsorbed by the liquid mass and recast in depth. Only with further cooling of the planet must those fragments have become numerous and large enough to form a first solid envelope, that is a true primitive crust. That first crust must have appeared as an expanse of very hot rocks, a few hundred degrees, interrupted by numerous large fractures, from which huge amounts of magma continued to rise. But just when the cooling process was leading to a crust increasingly solid and extended, the Earth, along with the other inner planets, was brought back in time by a particularly destructive event called intense late bombardment. About 4 billion years ago, in fact, large planetoids suddenly began again to bombard our planet, opening new tears in the crust, immediately invaded by magma. The phenomena seems to have originated from an instability in the asteroid belt, in turn caused by the migration of the gas giant planets towards their current orbits. The traces of that intense meteorite bombardment, which lasted for at least 300 million years in the period between 4.1 and 3.8 billion years ago, have been almost totally erased on Earth by weathering. But they are perfectly preserved on the Moon and many other solar system bodies in the form of impact craters and huge basins filled by lava recalled from the depths. According to recent estimates, in that remote area, the Earth was bombarded by about 70 planetoids of at least 10 kilometers in diameter. That is, by asteroids as large as the one that in the future would single-handedly wipe out large reptiles from the face of our planet. It goes without saying that the mass diversion of a large number of icy planetesimals towards the innermost regions of the system, therefore always towards our planet, can be a plausible answer. Even if it is not the only one and maybe not even the best one, to those who ask themselves where the terrestrial water could come from. These giant impacts also had the effect of awakening on Earth a paroxysmal volcanic activity, which most likely had a fundamental influence on the formation of the Earth's atmosphere and the oceans. Gases such as ammonia, hydrogen, carbon dioxide, methane, water vapor, and other elements were released from the incandescent rocks in the Earth's mantle, and gradually formed the primordial atmosphere within 100 million years. An atmosphere incredibly similar to that currently present on Titan, the largest of Saturn's satellites, and in any case extremely toxic to life as we know it today, being largely made up of a dense fog of gaseous organic substances. The primordial atmosphere of our planet was made up of a kind of aerosol of methane and nitrogen compounds, which could have caused a greenhouse gas warming, preventing the planet from reaching too low temperatures. And this calming function was largely due to volcanic eruptions that injected billions of tons of methane into the atmosphere. At the same time, on the Earth's surface began to occur another impressive series of events, which led to the formation of sedimentary rocks through processes of erosion, transport, and accumulation. These processes became fully active as soon as the surface cooled enough to allow the water cycle to take place. In fact, the primitive Earth remained for a long time shrouded in darkness, under a thick cape of dense burning clouds formed by water vapor continuously poured into the atmosphere from volcanic exhalations. When the temperature dropped enough, the clouds began to melt into rain, and the primordial atmosphere gave rise to storms of unimaginable proportions, under which the Earth groaned and boiled. At first, falling on the incandescent rocks, the rain evaporated, but with the gradual cooling of the solid crust, evaporation slowed until the water could condense in the most depressed areas of the Earth's surface, forming the first oceans, while the rocky plateaus formed the continents. On them were also formed the first river networks, which carried the debris torn from the higher areas and poured them on the bottom of the primordial seas. Gradually, our planet took on an aspect more familiar to us, with a gaseous zone rich in clouds called atmosphere, a liquid one with oceans, lakes, and rivers called hydrosphere, and a solid one indicated with the name of lithosphere, with the first sketches of those that will become the future continents. More recent studies have instead assumed that part of the water on Earth has been generated 4 billion years ago by the impact with asteroids, comets, or other icy celestial bodies. The theory of a cometary bombardment is supported by the fact that comets would have nuclei rich in water in the solid state, and the fact that the isotopic ratio between hydrogen and deuterium of marine waters would coincide with that of water present in comets and some asteroids. However, many astronomers disagree with this theory, since it would be demonstrated that the water contained in comets does not have characteristics similar to those of our oceans. Other researchers also say that the presence of water in the solid state on comets and asteroids is not at all obvious, and if there was, it would be in a quantity so negligible to defeat the theory of a cometary bombardment at the base of the origin of oceans. The last theory assumes that water, initially, was already contained in some types of rocks made of particular compounds, silicate hydrates. Within about 1 billion years, these compounds would have begun to release water, giving rise to a kind of primordial ocean. But if the water had origin on the surface of the planet already during its formation, it is possible not only to assume that life has appeared much earlier than what has always been thought, but also that other rocky planets have seen, during their history, the presence of oceans on their surface. However, even accepting this hypothesis, it is not excluded that other water has come to Earth from comets or asteroids in later times. Regardless of what is the exact theory on the origin of the oceans, it is widely believed that in these very first masses were born of the first forms of life. It is assumed that the first molecules, formed by carbon atoms combined with other elements such as hydrogen, oxygen, and nitrogen, were formed in the so-called primordial soup, an aqueous mixture of inorganic salts and various simple chemical compounds based on carbon, hydrogen, oxygen, and nitrogen, both organic and inorganic nature. In this mixture, energy inputs from the outside, solar ultraviolet, lightning, etc., would have led to the synthesis of a quantity of small organic molecules that would then accumulate in the ocean, giving rise to the first cells. The oldest imprints of life on Earth have been left in rocks 3.8 billion years old by microscopic living organisms that can be considered bacteria because they derive the energy needed for their life processes from the transformation of sulfur compounds produced by volcanic activity on the bottom of the oceans. Later, about 3 billion years ago, these organisms acquired the ability to obtain energy directly from sunlight and to accumulate nitrogen. Earth, our planet, was now formed and alive, ready to support the formidable biological explosion that would make it the most precious jewel in this part of the galaxy.